core, we have these high-level APIs. One is called Keras, and many of you are very familiar with it. It's a really, really popular, very intuitive and easy-to-use API for building machine learning models using high-level functional building blocks. Right? So with the recent releases of TensorFlow, we have made tf.keras as the default high-level API for TensorFlow. So very tight integration between Keras and TensorFlow, and we encourage all our new users to get started with using Keras-based model definition. In addition to Keras, we also bundle a lot of prepackaged models. This is the previously known sort of estimator framework that many of you might be familiar with. And the idea behind these is that these are models that have been developed and battle tested at scale, and they help you do your job sort of out of the box. So for both of these APIs, you funnel in your data using the tf.data API. And this makes use of feature columns. It makes use of very efficient data pipelines to get data into your machine learning models very efficiently. And then recently we have released a new API called distribution strategy. So this is a unified and easy to use API for setting up your training jobs on a variety of configurations of infrastructure, such as CPUs, single GPUs, multi-GPUs, as well as TPUs. And later today, Priya will give a talk where she will describe this API in more details. So once we have our training completed, then we can save our trained model in a format known as the TensorFlow saved model. And this basically saves with it the model architecture and the weights associated with it, which then allow you to later on use this model in inference or prediction. And then for deployment, there is a wide variety of choices, which is part of the strength of TensorFlow, that you really are able to use your machine learning wherever you want to use those algorithms. So you can use TF serving to deploy it in production. We have TensorFlow Lite, and Andy Selly will be giving a talk on this later to describe this in more detail, how you can take a TensorFlow saved model and put it on mobile and other embedded and IoT devices. We recently released a new library called TensorFlow JavaScript, which basically brings machine learning to the browser and to the JavaScript community with full compatibility with the rest of TensorFlow. And then we have a resource called TensorFlow Hub, which is a very nice repository for storing TensorFlow models and subcomponents of models, which we call modules, for easy reuse and modularity purposes. So all of this is sort of the TensorFlow core API framework, and this kind of shows how these different components work together. The other point that I wanted to highlight is that some of you have probably heard about things like graphs and sessions. And we've consistently got this feedback that TensorFlow was very complicated for new users to start with. Very non-intuitive. The code style did not make sense for people who are familiar with Python style programming. So one thing that we have done over the last 1 year is made eager execution more and more a central feature of TensorFlow. And the idea behind eager execution is that you write code imperatively, it executes as you write and run it, and then when you need the performance of graph, there are these tools that let you switch between this imperative programming into graph mode. And again, we'll cover this in a lot more detail later today. One thing to point out though is that with TensorFlow 2.0, which will be coming out sometime next year, eager mode will be default in TensorFlow 2.0. So this is going to be the recommended and the default experience for users going forward. So switching gears and talking a little bit about platforms that TensorFlow supports. It runs on a wide variety of platforms, from CPUs, GPUs to very high-end TPUs, and then on mobile devices, both iOS and Android, and other types of IoT and embedded devices such as Raspberry Pi. And we are continuously adding support for more and more platforms. So let's take a look at TPUs. So on the high-end supercomputer end, Google recently released these specialized chips called cloud TPUs. The version 2 was released for public availability in the summer of this year. And these chips have been designed from the ground up for the machine learning workloads. So they are extremely fast for running machine learning models. And you can see some specs here, 180 teraflops for this board with 4 chips with 64 GB of high bandwidth memory. So let's see what's possible with these types of devices. Here are some benchmark results on the ResNet 50 model, which is a very commonly used model for image classification and used for benchmarking. And on a cloud TPU, on a single cloud TPU board, we were able to train the ResNet 50 model on the entire ImageNet data set for a cost of less than $40 with an image throughput of more than 3,800 images per second. And there is this new sort of benchmarking suite called DawnBench that Stanford University publishes, and cloud TPU performance of this ResNet model is ranked number 1 on that benchmarking suite. So really, really impressive performance, and TPUs are enabling all kinds of models, not just image classification, and you'll hear a lot more about this later today as well. So on the other end of the spectrum, for handheld mobile devices, we are seeing enormous growth in these devices. I think there are projections that by 5 years from now, there will be more than 30 billion of these devices in the world. And India is one of the fastest growing markets for mobile devices. So naturally, we are seeing a lot of interest in deploying machine learning models on these types of devices. So for that, we have the TensorFlow Lite library. And here's a simplified architecture of how that workflow looks like. So you take TensorFlow and you train your machine learning model, you get a saved model, and then there is a topo converter or TensorFlow Lite converter, which basically takes that TensorFlow saved model and converts it into a format that's compatible with TensorFlow Lite. This model is optimized for power consumption, memory size, etc. So it's really tuned to run efficiently on a mobile device. And then you install this model on a mobile device, and there is a runtime for TensorFlow Lite interpreter, which is also installed on the device. And then using this, you can have machine learning on mobile phones. Depending on the device you're using, it interfaces with the underlying hardware acceleration layer, which will be device specific. So here's a quick video showing this in action. What you're seeing here is a image classification model that's been deployed on a mobile phone, and it's recognizing common office objects that are coming in front of the camera. So you see the Post-it, you see scissors, and the predictions are coming up on the screen, and you see the TensorFlow logo, which is very commonly found in all offices, obviously. So let's talk a little bit about programming languages and how TensorFlow can be used. Here again, we have a very, very wide range of choices for programming interfaces for TensorFlow. Of course, Python continues to be the mainstay. Most machine learning is still being done in Python. But there is support for all of these other languages, and most of these have been added and built by the community outside of Google. 2 languages that I want to specifically mention are Swift and JavaScript. So Swift support was added earlier this year, and this is something that is very exciting because Swift offers some very unique advantages in terms of a very intuitive programming style, yet advantages of performance of like a compiled language, and so it is a framework that has a lot of potential. And Google today is going to give us a talk on TensorFlow for Swift, and if you are interested in this, you will really want to see where we are heading with this. TensorFlow for JavaScript I mentioned earlier. So I don't know how many web developers or JavaScript developers are in the audience here. Just show of hands, how many JavaScript developers? Okay, quite a few. So for all of you out there, we have launched TensorFlow JavaScript. And the idea is that browser has some very unique properties in terms of interactivity with which it has a lot to offer for machine learning. Here's one example. This is called TensorFlow Playground, and many of you might have seen it. In fact, many of the online education courses on machine learning often start with this particular UI for interacting with the machine learning model. So in this case, this tool lets you configure a very simple multi-layer neural network, and you can interact with it, you can play with its hyperparameters, and you can see convergence, and you can see how the model is behaving. And this is all executing in browser using JavaScript, using TensorFlow JS. And we'll talk further about this. So let me talk a little bit about some of the tools and resources that we have. One of the tools that comes standard with TensorFlow is called TensorBoard. This is again one of the differentiating features, which is a very powerful plugin-based environment which lets you explore and visualize your model, to look at model convergence properties, to look at model structure, and to explore your data and try to find patterns in data. So what this visualization is showing is this is the MNIST data set, which is the handwritten digits data set. And you're seeing the TSNE visualization where the different data points with the different labels sort of clustered together in this sort of a high dimensional space. So TensorBoard is very powerful for debugging and prototyping your work. So in addition to deep learning and core sort of neural network-based methods, which continue to be the most widely used features of TensorFlow, TensorFlow also has a lot of packaged models that do classical machine learning, things like linear models, regression models, random forest, decision trees, gradient boosted trees. All of these are available for use in TensorFlow, and that collection is steadily growing. There's also a library called TensorFlow Probability. So those of you who are using any kind of Bayesian analysis or statistical analysis and trying to combine probabilistic based methods with machine learning, TensorFlow Probability has a lot to offer, so I encourage you to check it out. And then lastly, there are a bunch of research models that are all continuously being added on top of TensorFlow. And one particular library is called Tensor to Tensor, which packages many of these models from GANs and reinforcement learning and other sequence-to-sequence models and many more research models to really push the boundaries of what you can do with ML. So we talked a lot about ML model development, right? But machine learning is a lot more than just the model part of it. And anybody who's doing machine learning in production knows that. Right? There's a lot of other things you have to deal with. So towards that end, we recently released in open source TensorFlow Extended. So this is a collection of tools that lets you deal with the parts that come before the machine learning model. So bringing in data, data validation, and then once your model is being trained, doing things like model validation, model evaluation, as well as TensorFlow serving for deploying the model in production. And we'll hear more about how to use these very powerful tools to build complete end-to-end machine learning pipelines. And I mentioned TensorFlow Hub earlier. This is again our central repository where you can go and find a lot of reusable modules to do your machine learning work. So just looking ahead, where we are heading with all this, there's an enormous momentum in the team, as you can see from all these charts. We are getting ready to launch TensorFlow 2.0. And with TensorFlow 2.0, our biggest priorities are to make sure that all of these things that I talked about, they work better together, they work in a more easy to use manner, so that the APIs are simple, natural, intuitive, and we remove friction between all of these different components that are there today. And the other part that we really want to emphasize is that we are doing a lot to become more open and transparent. We are working on public design reviews, we are working on forming special interest groups where the ownership and leadership of taking a feature and driving it is out with the community, and we are very excited to see the growth of all of this. So I've given you a quick overview of where TensorFlow is and where we are going, and I'll turn over now to Amit, who's going to talk to you and sort of dive deeper into the details of our high-level APIs. Thank you so much.
Thank you, Sandeep. Before I get started with my talk, I just had a couple questions for the audience. So how many of you have heard of eager execution before? Ah, fantastic. And how many of you have trained a model in eager execution? Okay, perfect. So today, this talk will give a complete example. For those of you who are familiar with TensorFlow, you might see some new and improved practices here in our latest versions. And those of you who haven't trained a model as well, we'll be walking through one step by step. So building a machine learning model is a multi-stage process. The starting ingredient maybe is a CSV file of data. The end goal is to export a working model and serve it. And in between those endpoints, you have to load your data, prototype and evaluate different model architectures, and you may even have to redo the entire process if your features and your data change. So TensorFlow high-level APIs will help you throughout the entire process with functions and classes for every stage. And today I'll be walking us through a basic example using tf.data and tf.keras high-level APIs. I'll also cover some other APIs that will help you package the models we create. So one of the most exciting areas that machine learning is impacting is healthcare. TensorFlow is being used by doctors and researchers to find malignant skin cancer earlier and diagnose diabetic retinopathy. And we've discovered that looking at scans of the human eye, we can actually assess a person's risk of a heart attack or stroke. And this information was not known before. Just imagine, if this screening can be done on a mobile device, how profound the effect is going to be on the human population. Suddenly the whole world will have access to to rapid and affordable non-invasive screening for heart disease. So that being said, the data set we'll be working with today is the Cleveland VA Medical Center heart disease data set. So this is a simple binary classification problem where we have a really interesting combination of real data, categorical data as well. And we'll basically be figuring out whether a person has or doesn't have heart disease. So the first thing you do is a simple import statement. The next thing is enabling eager execution. TensorFlow is famous for representing computation with graphs, but it can also now be executed eagerly. When writing graph code, you execute the code that builds a graph with tensors and you execute the code later, but you build the graphs and tensors and operations earlier. Eager execution is more Pythonic. With eager, operations execute on tensors immediately. Eager execution, as Sandeep mentioned, will be enabled by default in TensorFlow 2.0. So here's a quick example of eager execution. Earlier, you would need to call session.run, but now you can simply just do the actual operation and you can print the output immediately. So with our data set, let me explain the features really quickly. So when I refer to them later, you know what I'm talking about. So we have stuff like chest pain type, the resting blood pressure, the cholesterol, and some other various categorical and integer features. The 11th feature is really interesting. It's actually a string feature. It's the result of a thallium heart scan, and the label is either 0 or 1. So that's exactly what you'll be seeing as we walk through the model. So here's what the data looks like. And I want to show you this slide because I know most of you must be having your data processed this way. And what's really cool about Eager is that we can import this, and the new TensorFlow APIs is, we can import this directly. We don't need to do any pre-processing on this data and normalize anything. All of this will happen using the APIs. So the first thing we're going to want to do is load our data in and process the data and the columns so that we can feed it into the model. This data set is a CSV data set, and we'll use the TensorFlow CSV dataset API to load our data from disk. It's in Contrib right now. We're soon going to be moving that to core. And the fantastic thing about eager execution is we can actually immediately check the values of the dataset object. So if we print the first element, we actually can see the first line, like 63, 1, 145, the last value is fixed, and the label is 1, so this represents someone who has heart disease. This is analogous to the first row in our data set. So eager execution is super helpful for debugging I/O issues such as invalid dimensions and formatting. So we have a list of 14 values without any structure, and we want to separate and format our data into features and labels. So we need to write a function that will map our old data set object into a new one, and will be applied efficiently by tf.data at runtime. So this function is normally where you can put image processing or other transformations you want to do to your data. And you might be wondering if we want to format the words into integers, but we'll get to that in a second. So in our parse CSV row function, we're just going to split the 13 features, and we're going to give them as the first element, and then we're going to provide the labels, which is the last element in the array. And we're going to return that tuple with features and labels. So tf.data.datasets have many great built-in functions that can shuffle and map and batch your data for you. And using this class actually allows you to take advantage of performance optimizations that are built in. So let's take a look at what your data looks like right now. As you can see, it's been separated into a tuple. The first is the dictionary that maps feature names to the vector of the actual values, and then the second element is the vector of the labels. So let's look at our multi-stage process and see where we are. We've taken our raw CSV data, and we've actually turned it into a tf.data dataset object. So now we're going to move on to creating our model. So when we saw the CSV file in our minds, we knew immediately how to represent the data. Like age, for example, we knew is a linear numerical value. but the way we represented gender as 0 or 1 is not. And so feature columns serve as an intermediary between the data and our model. They don't hold any data themselves, they just transform the data from numerical representations into data science concepts. Data comes in all sorts of representations and cannot be treated the same. And feature columns are a great way to standardize your data. So you can use numeric columns, which are types of feature columns, to represent age, income, and weight. You can use bucketized columns if your data has years and you want to bucketize them into different decades. You can use categorical identity columns, so for gender, 0 and 1, or categorical vocabulary columns if you have a list of countries. You can also do interesting things like hashing the column, like hashing different object names where your vocabulary size is huge. Or you could do a crossed column. So if you want to combine age along with gender, feature columns are a great way to do something like that. So remember our thal feature was a type of defect that we saw in a thallium part scan, and we have it represented by one of 3 possible strings. We would use the categorical column with a vocabulary list, and we have our list, normal, fixed, or reversible, and that's going to import the strings into numeric representation. And then we're going to convert that feature column into an embedding column, and you can convert it into any dimension, like so. Feature columns can be exported to save model, which is the save model format Sandeep was talking about earlier, but I'll get back to that more in a second. So the numerical features are simple. We just use a numerical column like so for age. And so now that we have our feature columns in a list, how do we add that to our model? It's actually really simple. We're going to use something called a feature layer. So for those of you who have used Keras, you might not have seen this. This is coming up in version 1.12 and definitely in version 2.0. When we train our model, this feature layer will act like any other layer, but it will take the dataset object and transform it into the format that the neural network is expecting. This layer also handles creating and training any embeddings that we have. And so oftentimes you have data that needs to be transformed into models. Feature columns can handle those with good performance batch by batch, rather than having a separate pipeline to do transformations when you're training, which could really impact your performance. Cool, so on to building the model. We're going to use tf.keras to build our model, and we're going to use the sequential class. And as you can see, we're creating the model literally in one line. So we're, our first layer is the feature layer that we discussed. We have a second layer that's just 128 hidden units, third layer that's 64 hidden units, and then we're applying the sigmoid activation function on our final output layer. So now we need to choose an optimizer and a loss function that tracks how well our model is performing. So I've chosen the binary cross entropy loss and the atom optimizer. And TensorFlow supports a lot of different optimizers and loss functions, so all you have to do is just change them and plug and play. Cool, so where are we in the high-level scheme? We have now created our model and informed it of what type of data to expect and how to read it. So now we're able to move on to training and validation, which is the most exciting part of this whole process. So training a model. Now this is a fairly small data set, so we don't need any hardware accelerators, but if we did connect a GPU, it would be fairly simple, and I believe that'll be covered in a talk later today. As for this particular case, in just 20 epochs, I was able to train the model to around 84% accuracy. So it's just as simple as a simple for loop and then calling model.fit. Now we want to check our results on a test set or validation set. So we're going to create a data set again using the test CSV file. So as you can see at the top, we've kind of done the same thing again. We've created a CSV data set, we've mapped it. And so hold on to that. We'll be creating a load function, which I'll reference later on. And so since I have 50 examples, like I said, it's a small data set, I create a batch of 50 and run once. And my accuracy is around 84%, where I got lucky. But a fun exercise might be to see how you can take this data set and see how you can get the accuracy based on different models. All right, back to the grand scheme of things. So we have created and validated our model, but that's useless to us unless we can export it and deploy it. And there are a lot of ways you can deploy a TensorFlow model, and more details of those will be covered by the TFX talk later today. But right now, I just want to talk quickly about saved model, which Sandeep mentioned earlier. So what is saved model? It's exactly what it sounds like. It's a model saving format, which now supports Keras models as of 1.12, version 1.12. It's as easy as calling this function, and you'll notice a directory is created with the following information. And in the directory, you'll see a object-based checkpoint file created with tf.train.checkpoint and a saved model proto file as well. And unlike HDF5, saved model actually works out of the box with TensorFlow systems such as TF-Hub and Servomatic. And if you want to, on the flip side, if you want to restore the model, you can just make this simple call and treat it just the same way we had the Keras model earlier. So that's it. We started from a raw CSV file, and we have a working model. But the story hardly ends here. You know, with 84% training accuracy, we're essentially misdiagnosing every fifth patient, and that's hardly a good idea when it comes to something as serious as heart disease. So how can we improve? You know, we can go and collect more data, and we can make cross-feature columns, and we can add and remove layers. We can use different model types. But I'm going to quickly show you another API that's great for, you know, trying different model types really quickly and comparing them to this result. So this is what our deep model looked like using tf.keras.sequential. So we're going to use something called estimator now. Have any of you used estimators in the past? Cool, so quite a few of you. So estimators, canned estimators are pre-made implementations of machine learning algorithms. And here are some examples of the canned estimators that we support. And for our data set, I'm going to try the wide and deep model. So the wide and deep model combines a traditional linear model along with deep learning, so we can feed different features into different sections of the model. And with the estimators API, it's really simple. All you have to do is call the tf.estimator class, and then we can provide the linear feature columns that we wanted. And remember, these are the feature columns we created earlier. And we can provide the neural net feature columns that we want, which might be something like age, like the integer columns. And then we specify the hidden units and the number of classes that we have. And one thing about estimators is that they expect an input function to provide them the data, and estimators run their own sessions and graph logic. So remember the couple of lines I mentioned earlier that we turned into the load data function? We're going to provide that to model.train. And every call will essentially return a data set batch of whatever size that you want. And we'll do the same thing for our test data and feed it into an evaluate call rather than a train call. And now we can run the wide and deep model, same way we ran the Keras model. For this one, we got 81% accuracy, so it wasn't as good as our original Keras model. But the point is, it's really simple to try different models using canned estimators and then compare your results across the model. You've already done most of the heavy lifting using the data preprocessing and tf.data, so you just have to use estimators to try all these different hosted models. And just the same way we exported Keras models, we can export estimator models and serve them as well. And you may be wondering, how do I take live incoming data and give that to the model? So for that, we can use a function like this, build raw serving input receiver function. And it's kind of it needs to know what type of format the data is going to come in. And that's why eager execution is great. All you have to do is take the first element of the data set and provide it to the function so it understands how you're going to be getting the input data. Then we export it to saved model like so, just as we did with Keras, and we can use this model in tf.serving and tf.hub. So yeah, just a quick overview of what we covered today. We learned how to prototype and build basic initial models and play around with eager. We learned how to pre-process data from CSVs using tf.data and datasets, which are extremely powerful MLIO tools. We transform data from random values to dimensions and tensors that the model can understand using feature columns. We built a simple working model with Keras. We use the estimators API and canned estimators to compare different types of models really quickly across the same data. And we packaged with saved model and exported it out to whatever serving platform we wanted to use. So yeah. And most of the time, the incremental improvements you'll be making will be happening around the last 3 steps. And nothing is ever perfect, so you'll always be trying to improve. And if you have reached 100% accuracy, you are testing on your training. So, yeah. Thank you very much. I'd like to give a huge shout out to Carmel, who was my colleague Carmel, who was a big contributor for our talk. And I would like to introduce Wolf, who will be talking about autograph.
Not live yet. Here we go. Hi everybody, I'm Wolf, and I'm going to talk to you about autograph. How many of you know what autograph is? That's like 0. Oh no, there's like 4. All right, great. Good. This will be fun. So graphs have been the basic form of interaction with TensorFlow for a long time, and they have plenty of advantages. Graphs simplify deployment to all kinds of environments. They can run, they're just like a platform-independent view of your computation that can run on CPUs, GPUs, TPUs, mobile devices, Internet of Things, in your browser with TensorFlow.js. And in a data flow graph, dependencies are explicit, which makes it pretty easy to run in parallel and distribute the computation. Graphs also allow for whole program optimizations, like kernel fusion, where you replace certain subsets of your graph with like fused ops and things like that. But creating graphs is not always easy. Much like constructing an abstract syntax tree programmatically, it is a tedious task because you have to write lots and lots of verbose API calls. For example, if you look at this example, we have a lot of boilerplate, which is actually this really simple, like y equals mx plus b kind of computation. On top of that, computations are deferred. So when Python executes tf-matmul, you don't actually get any computation. You just get the op back that you can call later. You have to call it later with session.run, and that's when the results are actually calculated. So when you're doing this kind of meta-programming problem, it's a little bit hard to have insight into what's going on. Control flow is especially unnatural. I can say the very first thing that I tried to do with TensorFlow was to ingest a whole bunch of JPEGs and try to figure out if they were portrait or landscape, which meant I had to dig into tf-cond. Anybody a big fan of tf-cond? No, probably not. If you try to write this in TensorFlow like this if gets executed at graph creation time, which is not what you want. So instead you have to convert it into this thing on the left, which it's got a lot of extra boilerplate and it gets kind of redundant because you have to describe all of the syntactic stuff with Python API calls. One answer to this is eager, which we just talked about, which has a lot of the shortcomings, which addresses many of these shortcomings. It achieves that by executing operations immediately, so it's sort of like using NumPy. That comes at a price though, because you're giving up graphs now, which means you've lost all that cool optimization that we just talked about. The verbose graph code, if we use eager, the verbose graph code that we have here has gotten a lot simpler. In additional benefit, control flow becomes much easier to understand because the actual value of the tensor is known when we do that if x equals greater than 0, x is no longer just an op that you got back, it's the actual value. If you like programming in eager, and it sounds like fun, just as a side note, like this is the URL that'll get you started on it. So if we compare eager and graph computation, eager mode lets you write more or less standard Python code with standard control flow syntax, but you lose some of the benefits. For example, eager code cannot yet be run on TPUs, and there's no opportunity for whole program optimization. Graph mode is more powerful, but more difficult to write. If you want to benefit from both approaches, you can imagine using eager mode when developing prototyping, and then you switch to graph mode when you want it to go really fast or you want to distribute the computation. One piece of that puzzle is called defun. It's a Python decorator that wraps a function, and it's a way of declaring that this snippet of code should be bundled up as a graph. Within that snippet, you get back the portability and performance benefits of graph mode. The way this would work is you prototype using eager mode, and then when you're done, or you want to scale this up or productionize it, you wrap it in defun, and then you get this graph back. But there's a catch, because if you wrap it in defun, now you're back in graph land, and you're going to have a lot of trouble with these if statements. You'd have to rewrite them all as tf-const. We have another piece of this puzzle. You could use pyfunc. With pyfunc, it allows you to go from graph and drop down to Python. Pyfunc doesn't really solve all your problems, though, because pyfunc actually just runs in Python. So if you're running on a mobile device or something like that, you don't actually have Python, so you can't actually fall back to Python. It's also not necessarily very fast. So whichever way to go, you have to make a compromise of some kind. Ideally, you want to have benefits from both sides. You want to be able to write the code that you see on the left, and then get the performance of the code that you see on the right. I wonder, though, is there some way we can get the benefits of both? Autograph. Write eager style code, and generate graphs anyway. What autograph does is convert the code on the left, your left, my left, and the code on the right. If you look carefully at the two pieces of code, you realize that one can be transformed to the other pretty mechanically. And that's what autograph does. So if you want to use this, all you have to do is write this special annotation, autograph convert, and that function will get converted. So under the hood, it gets this, if x equals whatever, gets converted to this nice autograph generated code. And in fact, you can actually inspect it just by saying autograph convert instead of autograph code, to underscore code instead of autograph convert. Here's another more complicated example of an RNN. And this RNN actually does a bunch of stuff, right? It's got these inputs, and it's dealing with variable length sequences, and it's looping around. The code is actually pretty natural looking. It looks like normal Python. It lets you use all kinds of TensorFlow APIs. So if I wanted to, with the autograph convert, this sequence of code here turns into this, which, as you imagine, would be a lot harder to write. So it's a really good thing that we have autograph that makes you so you don't have to actually figure this stuff out. What else can autograph do? We've seen a few examples of ifs and fors. Autograph converts print statements too. And inserts the control dependency, control underscore dependencies to ensure that everything gets kind of computed in the right order so that you can print things out correctly. It converts assert statements, which is really cool. Turns asserts into TF asserts. You can use it to convert not only functions, but entire classes. It will recursively convert things that are inside it. And you can convert arbitrarily nested control flow. So like if, and then another if side, another like that, and we'll handle things like break and continue. And we're working on making even more things in autograph. How many of you remember or know about FizzBuzz? This was like in the 90s, this was like every programming interview was like, can you write FizzBuzz? It's a really simple game. The idea is you iterate through a list of numbers and you say fizz whenever it's divisible by 3 and buzz when it's divisible by 5. So this is how you would just write it in Python. And with tensor operator overloading, it's just going to work, except for all of this control flow. So let's look at the control flow graph after we convert this with autograph. You ready? It's going to get exciting. You get that, and you get that. So if this were a programming interview question, you would not be able to get that right in 15 minutes on a whiteboard because you're a great programmer. So autograph just turns that 10-line Python thing into this mess, so you don't have to. So let's take a closer look at some of the more interesting tricks that autograph uses. One of the ways to think about autograph is sort of operator overloading, taken to its logical extreme. So you probably know about operator overloading. Whenever you're doing tensor multiplication, we've overloaded the star operator with underscore bool underscore. And then we can customize the behavior of multiplication. So when you write C equals A times B, that turns into TF multiply, which is why most of the time you don't have to write TF multiply anywhere. So that's good. Arithmetic expressions are pretty easy to write. But Python doesn't have built-in facilities for overriding control flow. So if I wanted to overload if here, it's not going to work. So with Autograph, we use code rewriting techniques to implement these overloads anyway. So somewhere in Autograph, we have facilities to replace Python statements with our custom functions, and we use them to overload the control flow. So if we convert all the if statements in your code, but one question you might ask is, should we convert all of our if statements? For example, in this for loop, the if statements at the top shouldn't run in the graph because they're actually setting up the graph. So there's a decision to be made. Do we transport a piece of code or leave it as it is? If we knew the data type of the variables, we'd be able to tell. For instance, if the variable involved is a tensor type, we run the computation in the graph, and otherwise we run it in Python. But the problem is, how can you tell if a variable is Python, or it's supposed to be Python, or it's supposed to be tensors? This is Python. Python is dynamic, it can be anything. So if we can't make our decisions by analyzing the code, we'll just do it at runtime. So we use a trick called dynamic dispatch, which conceptually looks like this. Simply put, it means in our custom operators, we first look at the data type, and if it's a tensor, we create a graph, and if it's a tensor, we just do the regular thing, and if it's a graph computation, if it's a tensor, we create a graph computation. And if it's not a tensor, we just run it like a normal Python if. This ends up looking a little bit like lightweight modular staging, which is something you can look up on a search engine of your choice if you want to learn more. Okay, so we know how to overload ifs and whiles, and we can do it dynamically, so we can be smart about it. What about things like break and continue? TensorFlow doesn't have break and continue ops, so we have to do something about that. We can use a different trick. We can replace break and continue with a few well-placed conditionals, and then just turn it into while loops. And then we get to apply, just use our usual tools. So here's a couple more canonicalizations that we do. In addition to converting break and continue, we also convert inline ternary operators, list comprehensions, multiple returns, and we can homogenize for loops. Every kind of loop just turns into a while loop, and that makes it easier to convert. So as you can imagine, rewriting our source code can make it harder to debug when you get errors that's kind of bad. So we have to be extra careful to make sure error messages aren't just hopelessly terrible. We already have this problem in graph style Python. You know, like when you write Python that generates a graph, something goes wrong at runtime, you have to point back at the original code and say this was the piece of the graph construction code that went wrong. And TensorFlow actually does a pretty good job of taking these runtime errors and tracing them back. But that's one layer. But with Autograph, we actually have more layers. First, Autograph compiles into Python code, and then the compiled Python code runs, and then finally TensorFlow runs the graph. So this is something we're working on, but in short, we intend to make this, when you get a runtime error, point back at the original piece of Python you wrote, so you aren't looking at some gigantic stack trace that's inside this generated code. Forging stack traces is kind of difficult, so we're working to make this better. So that's kind of where we are. This is kind of the status that we have. We have a public beta that we launched in July. We're working with, we're trying to get Autograph and Eager together so that you can use them in Eager to get performance right there without having to switch back to graph execution. And then you can kind of seamlessly accelerate parts of your code with defun and Autograph. We'd also like to, we're also going to release, we'd like to release a separate Python library that does this kind of operator, sort of supersized operator overloading as a separate library, because that might be fun for your own applications too. And if you have other things, if you start using Autograph and you start converting all your cool whiles and fors and RNNs and everything, tell us what you want, because then we know what to do. All this talk of defund and Eager makes me just want to pause for a minute and talk a little bit about TensorFlow 2.0, because we kind of hinted at it here and there in the previous two talks. So who's heard of that we're going to have TensorFlow 2.0? Yeah, all right, a bunch of you know that there's TensorFlow 2.0. Let's just talk a little bit about that, because it's kind of an exciting subject. So the focus of 2.0 is easier and more intuitive APIs. You just saw this, because we just did all this stuff with Eager and Autograph, which should make it easier for you to write your models. As part of an improved user experience, we also want to sort of pick kind of one save format, because right now there's a whole bunch. It's going to be save model, that's the intent. And for specialized use cases, we want to kind of break these out into other libraries, so like TF Lite and TensorFlow.js, Rather than making TensorFlow core get bigger and bigger and bigger, we want to sort of spin out some of these projects that do specialized things. That does mean between 1.x and 2.0, there are going to be some breaking changes, but these are all hopefully for good reasons. The main reason we want to make breaking changes is to enable a better user experience. One of these things is like eager, which we just talked about. There's also just some oddities in the TensorFlow API. For example, we have kind of inconsistent function signatures and argument names that are kind of hard to predict if you're just writing code sitting in the command line, and we want to fix that stuff up. The other thing is that because TensorFlow has evolved really rapidly over the last 2.5 years, there's like 2 or 3 ways to do a lot of stuff. We want to make it so there's only one. So we're going to collapse one of these. An example of that would be like TF layers versus TF keras layers. We're only going to have one, and it's going to be keras. So finally, there's going to be a couple of subtle breaking changes that allow us to do some optimizations that we can't do under the current semantics. One example of this is that we're going to switch a lot of these variables over to resource variables. This is like super subtle, and it probably won't affect everybody, but here and there you might see some breakage, and we'll have to look into it. So let's give you some examples of the kind of changes we're making. The biggest here is that we're going to enable eager execution by default. What that does is it replaces the TensorFlow graph primitive with TensorFlow functions. This will align the programming model and make it so reasoning about what TensorFlow code does easier. So code executes immediately unless you're inside a defun decorated function. The callable that the defun decorator returns is just like another Python function, but you can schedule those callables on GPUs or TPUs, or just execute them on CPU if you want. So just scattering of other changes, they're going to be resource variables. Like I said, all variables are going to be resource variables. Rather than having variable scopes to keep track of all your variable names, we're going to instead just use this using Python references. This will also make it much easier to figure out what's going on. I don't know about you, but you keep adding stuff to your graph by accident and you accidentally save it. This is going to be better. We're also going to get rid of collocate underscore with. It didn't seem to help that much. If it does help you, please come find me and tell me about it. But as far as we know, I don't think we're going to take it away just to help us do some optimization. And I think the sort of most far-reaching change, but actually the most I think the most easy to handle, is that we're going to refactor a lot of the ops and things into packages that have logical names. And the quintessential example of this to me is tf.log. Does that log something to the output, or is that natural log? Who knows? tfmath.log makes a lot more sense. So you might ask yourself, how am I going to upgrade all this code from 1.x to 2.0? We want to make this easy for you. And we've been through this once when we went from 0.12 to 1.0. We're going to provide like a binary or a script that is going to mechanically do a lot of this transformation for you, especially the refactoring of the op names. This won't be able to do everything for you, and in the cases where it can't, it's going to print a bunch of warnings and say, hey, we don't know how to convert this, but you should probably convert this. We're also going to keep a fully functional version of the V1 API in a compatibility manager. So you import TensorFlow, and then you import the compatibility module, and now you can talk as if you're in 1.x. This means if you don't want to touch your code at all, you just simply change the import to this compat import, and you're good to go. The difference is we're not going to keep developing the 1.x in the 1.x direction. So if you file issues there, they're probably going to be delayed in favor of fixing things in 2.x. So just to give you an idea of the time frame, let me give you the idea of the timeline. We've started design reviews and RFC. You can find it in our GitHub community thing. We're going to have a preview version of this by the end of the year, and there'll be like a nightly build that you can try out. In the spring, we're going to cut a branch, and we'll have a release candidate that we're pretty confident about, and then we'll have the final version not too long after that. So 2.0 is going to be fun. It's going to make it easier to write in TensorFlow. It's going to help us improve a lot of these things, and we need your help. The ways you can get involved is tell us, and also come talk to us about any concerns you have. And then check out the RFCs, GitHub, TensorFlow community. And once we have a preview, try it out. Tell us how it works. And that's everything I have. Thank you. So right now, we're about to head into a break. Right? Kartik wants
Yeah, I just want to make some announcements.
Yeah, Kartik's going to come up and make some announcements.